everyone. So I think we'll just start the class now. Um, yeah, we have four students here. Yeah, okay. I think more will join soon. So what do I have here is I thought I will revisit again a few problems or few concepts which we already studied in the previous you know previous week. So what I would do is today I'm going to solve two new problems, but it is going to be based on the same old concepts. But it will be useful for you to solve the week 3 assignments. That's why I chose this. We will talk about nozzles and its performance in the next week. Okay. So having said that, I have two questions today. One is about a single stage and two stage rocket, and then one another one is about calculating acceleration. Okay, so yeah, we'll go through that. Before I start, do you have any questions? If it's a quick question, I can answer. Uh, if it's a long, lengthy question, maybe we will finish this two questions and then may probably I will be done by, let's say, like next 40-50 minutes, and then we can discuss. We will have enough time, about 1 hour, to discuss. All right. I guess there are no questions. Yeah. So anytime you can stop me if you have any questions. So now I will go forward with the questions I have. So I hope I'm audible. Let me check my recordings. Okay. So the first question is about, consider a single stage liquid propellant rocket with a jet velocity of 4115 meters per second. Is used for a mission which has a velocity requirement of 14,300 meters per second. So basically, this is a delta V for a mission, and we are going to achieve it by a single stage liquid propellant rocket. Um Payload weight is around 900 kgs, and the structural mass ratio is given, which is around 0.03. So find the payload mass ratio and the initial mass of the rocket. What is the initial mass of the rocket? In addition, we can also find the propellant mass and etc. All the other masses. And now the next question was, what happens if two-stage rocket is used? So the first question is about single stage. Now what if I use two-stage rocket and use the same propellant, which means I will have the same jet velocity, and the velocity requirements is equally provided by each stage. So each stage will contribute to half of the velocity requirement. So if that is the case, what is going to be my payload mass ratio and initial mass of the rocket? How different it is going to be is what we are going to see. Uh, so uh, let's start solving it. So first, let's try to solve a single stage rocket. So first we will solve single stage rocket. So maybe what I could do is I could draw a schematic over here. This is the single stage rocket. It's going to be there's going to be only one stage, and gases are coming out. VJ, and have payload. Now, what are the things given is we have mass of payload, which we usually used to call it as mu, right? So useful mass, which is around 900 kgs. What is given is the jet velocity is also given 4115 meters per second, and the velocity requirements, the total delta V of a mission is 14,300 meters per second. Okay, and also structural mass ratio is given. I hope beta is the notation we use for structural mass, or basically what this means is the mass of the structure divided by the initial mass of the rocket, or initial mass of that stage, so which is going to be 0.03. Okay, and yeah, that's it. So what we are asked to find is we need to find alpha. Okay, which is nothing but payload mass ratio. This is what we need to find. What is this? And then we also need to find mi. Okay, I hope the question is clear. So basically we are telling we have a single stage liquid propellant rocket, and the jet velocity is given, and delta V is given, and structural mass ratio is given. We were asked to find payload mass ratio and initial mass of the rocket, which you guys know better. So um, then you guys can tell me how to solve this, right? So how can we solve this? Aditya, have a question. Sir, it is true that Swayam will only take 3 assignments which are best scores out of 8 for main result. I'm not sure about that, Aditya. You can go through over the NPTEL course details. There you will come to know, or you can email NPTEL about it. Okay. Okay. Coming back to this question, mm, how do we solve this? We are going to use rocket equation. So what does it say? Delta V is equal to Vj times ln of Mi by Mf. So this is what we are going to use. Only thing is, it's going. We will maybe change this a little bit. This equation you all know
So
this.
with this equation, we can find mi by mf of the rocket.
Right? Yeah, we can find Mi by Mf of the rocket, and after that we may need to find the other things, right? Do you have a question? Were you asking me a question, Akhilesh? Uh,
So I was just telling the
okay, okay,
method just now.
okay, okay. Haha, you are right. So we will just find Mi by Mf, and also we can get alpha and beta after that, or we can directly try to get alpha from here also. So what we know is you know for a change we'll just change this equation a little bit. Okay, so mass of final we know it's going to be ms structural mass plus the useful mass. So let's say if you substitute it here, then we can I hope you guys this even professor must have derived it, but for the sake of completeness I'm just writing it here. So you can write this as divided by mi, and this you can write it as Vj into natural log of 1 divided by ms by mi is beta, and mu by mi is alpha. So we can simply write alpha plus beta. Okay, so now what we know is we know delta v, vj and beta, so we can find alpha from here. So we can quickly find the payload mass ratio. Okay, so let's say if I want to rewrite this, I can write it as um, pi alpha plus beta is equal to exponential of delta v by vj, and alpha I can write it as 1 by exponential of delta v by vj minus beta. Okay, and hence this can be written as exponential of 14300 divided by 4115 minus 0.03. This is going to be the alpha. So can you guys find what is the alpha? So it's just straightforward algebra, so that's why I didn't go through it much. Let's say if I want to quickly calculate it. So if you guys know the answer, please let me know. So I'm getting something like 32.3 minus 0.03.
So it's coming 0.00096, like
Okay, so
three
maybe I
zeros
can
after the decimal. I
so
get this.
maybe I can write 9.6 into 10 power minus 4.
Minus 4. Yeah, yes, sir.
Okay, okay,
Exactly.
okay. So thank you, Akhileshwar. So this is the uh, what do you call payload mass ratio. So that is coming out clearly. So then you can write alpha to be mu by mi, and this is going to be 9.6 into 10 power minus 4. So then we can find mi to be 900 kgs, which is mu, divided by 9.6 into 10 power minus 4. So how much is this coming? This is the total mass of the rocket during liftoff. So
So it's coming 937,500 kg.
so maybe I can write it like 937.5 into 10 power 3 kgs.
Yes, sir.
So this can also be written as 937.5 tons. So this is the total weight of the
Okay.
rocket, okay, initially. Now, let's say if I want to calculate the propellant, how can I write propellant mass? Propellant mass, I can write it as mi minus the structural mass plus the payload mass. I can write it like this, right? This also I can write it like mi into 1 minus alpha plus beta. So I'm just taking mi out, so you will have ms by mi and mu by mi, which is alpha plus beta. So it's just straightforward mathematics. I mean, you guys are talented in that. So 1 minus alpha is 9.6 into 10 power minus 4 plus 0.03. Okay. So if that is the case, what is the propellant we have? So it may be something around 908.47, I guess, to 10 power 3 kgs. So you can see that the propellant required, the amount of propellant required is around 908.4 tons. So that is the amount of propellant required if you go for a single stage rocket motor. Sorry, single stage rocket. So let this be. Let's now what we should do. What we shall do is we'll try to find it for a two stage rocket. Okay. So let's go with the two stage rocket. So in a two stage rocket, what happens? Let's say if I want to draw a schematic, it might look something like this. It's just a rough sketch. Okay. So this will be our stage one, first stage, and then this will be our second stage, and then after that we have payload. So gases are coming out like this. Okay. So if this is the case, what has been given is we are going to take the same jet velocity, okay, for both the stages. So let's say Vj1 is equal to Vj2 is equal to 4115 meters per second, and the delta V is equally divided between these two stages, right? So we can write delta V to be equal to, I mean delta V1 equal to delta V2 is equal to, so 14,300 divided by 2. So each stage is going to give me around like 7,000, I guess 150, 7,150 meters per second. So this is the delta V each stage is going to give me. So ultimately I'm going to reach delta V of 14,300 meters per second. Now, um, if that is the case, what we are going to find out is we are going, and also it's given that beta 1 and beta 2, which means the structural mass ratio is going to be same 0.03. If this is the case, we are going to find out the total mass of the rocket and also the propellant, and we'll see which way of launching this payload is better. Okay, that is what we are evaluating. So now let's say for the stage 1, if I want to calculate, so I can calculate for stage 1, let's say if I want to write the equation, it can be something like this, uh, m I of 1 by mf of 1, which again can be written as vj1 into natural log of 1 divided by alpha 1 plus beta 1. Okay, I hope I'm clear till now. So now again we can rewrite this as alpha 1 is equal to 1 divided by exponential of delta v by vj1 minus beta 1. Okay, now say if I want to calculate alpha 1, how much that is going to be? So it's going to be 150 divided by 4115 minus 0.03. Is the alpha 1 coming around?
So 0.15, I guess.
0.15. Okay. Now, this is the alpha 1, which means the payload mass ratio in the first stage. Okay. Now, with this, let's say if I want to calculate, let me add one more. So, this alpha 1 is going to be simply the payload of my first stage divided by the initial of first stage, but mu1 we don't know yet because we don't know the second stage mass yet, right? So first let's try to solve the second stage. It's the same thing what we did in the last tutorial also. First again we'll go and first solve the stage 2. Okay, stage 2. For stage 2, again we will write the same equation, delta v2 is equal to vj2 none of, it is going to be mi of 2 by mf of 2. Okay, so if that is the case, we can write this as vj2 ln of 1 divided by alpha 2 plus beta 2. This is for second stage. Same thing, you can just rewrite this as alpha 2 is equal to 1 divided by exponential of delta v delta v2 by vj2 minus beta 2. So again, actually what we will see is, since delta V is equally divided between these two stages, this is going to be same, and Vj is also same for both the stages, and also beta is also same. So you will be end up getting the same alpha 2. Alpha 2 will be equal to same as alpha 1, which is going to be 0.15. Okay, but now what we know is at the second stage we know that the m second stage alpha 2, we can write this as useful mass at the second stage by initial mass at the second stage, right? So useful mass at the second stage is nothing but the payload, which is 900 kgs. So then we can write this as m 900 times mi of second stage, which is going to be equal to zero point 0.5. So from here you can find the mi of second stage, which is going to get which you can use.
6,000 kg or 6 tons, I guess.
Okay, 6000 kg, is it?
Kg.
6000 kgs. Yeah, thanks. So this is the uh, second stage mass, total mass of the second stage, which includes payload, right? Now this is going to be your payload for the this is going to be the payload for first stage. So that is what we are writing here. The mass useful at the first stage is equal to mi of second stage, initial mass of the second stage. So if that is the case, then you can write alpha 1 equal to, which is nothing but of first stage by initial mass of the first stage, can be written as mi of second stage divided by mi of first stage. Okay. So from here, how much are you getting? Mi of first
40
stage,
ton, 40 ton or 40,000 kg.
40,000 kgs. So now, uh, this is nice. Now let's try to calculate the propellant for the first stage. How do we calculate? We know mi of first stage minus structural mass at the first stage plus useful mass at the first stage, which is nothing but second stage's second stage's total mass. So this also again you can rewrite this as mi of first stage is 1 minus alpha 1 plus beta 1. So from here you can write this as 1 minus 1.1.5 plus 0.03. So how much is this coming out to be?
32,800 kg.
32,800 kgs. This is the mass of propellant you need at the first stage. Okay. And then what is the mass of propellant you need at the second stage? You can apply the same logic, mi of second stage into 1 minus alpha 2 plus beta 2. So that is going to be, I think this is around 6000 kgs plus 1 minus alpha 2 and beta 2 are same as alpha 1 and beta 1. So let's say if we do that, how much are we getting?
4,920 kg.
4920 kgs. All right. Now let's try to add all these things up. So the mass of rocket for the second stage, okay? Mass of total mass of the rocket, two stage rocket, okay? Total mass of two stages is what we calculated, which was around 40,000 kgs or 40 tons. Or 40. And the propellant, total mass of the propellant, total mass of propellant required is How much is this? It's around 36, 37,000. I guess something around that, right? 32,
37 720.
30,000
37
sound.
720.
37, 7, 10,
720.
20. 37, 720 kgs. Now let's compare both of them. Okay.
It's drastically less.
Right. So, any idea why it is drastically less?
So basically, what I observe at first is that the payload mass fraction has increased tremendously. So that's why
Okay. So, what do you think? If I keep on increasing the stages, will this keep on reducing?
it may for up to a point, I guess.
So, what could be that point?
I'm unaware of it.
Okay. So, what you can do is you can continue this for, let's say, three stages. You can continue this for four stages. You can continue this for five stages. Maybe you can write a simple MATLAB program or something, and MATLAB or Python, and you can find out what is the optimal point, but at what point it basically plateaus, or it even increases after a certain stage. The mass of rocket and the propellant keeps increasing. Okay, so let's say for comparison, let me write it down here. If I want to write it in terms of tons, I am having 937.5 and 908. So 937.5 tons, 908 tons, and then you have in two stage you have 40 tons, and in that 37.72 tons. All are in tons. Okay. So this is a decrease in terms of economic point of view, and also technology level. It's better to operate at multiple stages than as a single stage. Um, so that is why you will see rockets will have three or four stages sometimes rarely, but three stages in any rocket launch. So it's in order to reduce the mass of the rocket and also the propellant usage, and also this also help us increase in the payload also. Let's say 900 kgs. Let's say you have 908 tons of propellant. Let's say you can use 908 tons of propellant, then you no longer need to restrict yourself for 900 kgs of payload. You can increase your payload to, let's say, 1500 or even 2000 kgs. Okay, so that is one of the advantages it provides. And also we made few assumptions here which lead to this conclusion. One is the structural mass ratio, and another is these vj. uh, so usually what happens in any rocket, each stages would be little different. So for example, in, let's say, if you take a PSLV or GSLV, so in any rocket, what you will have is you will have first stage as a solid propellant. The motor will be the rocket motor, and the second stage and third stages will have liquid propellant engines, liquid propellant or cryogenic engines. So basically, both are liquid propellant engines. So these both will have different efficiencies. For example, it might have different VJs, ISPs, and also based on that, the delta V's also will vary. Okay. So in reality, the concept of designing this is actually a little difficult. So that's why people always so optimizing this is a multiple as a multiple variables in it. For example, the VJs will vary. VJ of each and every stages will vary. Delta V's of each and every stages you may need to optimize it, and also ISPs of each and every stages will vary. For example, solid propellant will have lower ISP and liquid propellant will have higher ISP. And also the uh, the design of the rocket. For example, you might have a smaller you might have restrictions in how much what is the amount of solid propellant you will be able to carry, what is the amount of liquid propellant tanks you may be able to carry. So those restrictions will pose a constraints on the thrust, essentially the thrust at each and every stages. So thrust also will not be same for each and every stages. So this is like an ideal scenario what we solved. Now all these things are variables which you can vary in order to optimize the, for example, performance, or you can optimize the cost. So that is what ISRO is so famous for. They optimize the cost to a very low value. That's why they are most efficient you know service providers for any satellite launch. That's why PSLV is still running for like more than 30, 40 years. So that is something I wanted to touch. That's why people go for two stage and three stages rocket motor. So let's say if you continue this, let's say you can take this as a homework, you continue this for a three stage and four stage. Doing it by hand might be little difficult. You can write a small program, um, and you can plot what is the mass of rocket, how it is varying, and what is the mass of propellant, how it is varying with respect to stages. Okay, and you can let me know. So maybe it might look something like this. I solved it long back. Um, so let's say if you increase the stages, and this is the mass of let's say rocket, what do you call of the rocket. What happens is after this is first stage, second stage, third stage, fourth stage, it might actually reduce it to third stage. Okay, and it might also reduce till fourth stage, but it becomes more complex as you keep increasing the stages. But after fourth stage, it will actually increase. But you no need to take my word for that. You can do it for yourself and let me know. Okay. All right. I hope you guys understand. Is there any questions regarding the first problem we solved today? I think in assignments you may need to answer the payload ratio, propellant ratio. I think all these things you will be able to answer it based on this. All right. I hope there is no questions. So if there are no questions, let's go forward and continue our discussion on. We'll solve another problem. Okay. And
Yes, sir.
okay. So what do we have here is the second problem is about a rocket of mass 1000 kg, okay, contains 1500 kg of propellant, which means rocket of mass doesn't include the propellant. Okay, the propellant is consumed at a constant rate of 100 kg per second. So the consumption rate of propellant is given. Find the acceleration of rocket at liftoff, okay, 10 seconds after liftoff, and just before the burnout. So we are requested to find acceleration at three different places. One is at the liftoff, 10 seconds after liftoff, and just before the burnout. So, and also we were asked to find the specific impulse of the rocket is given, and we were asked to assume that assume it is a vertical flight and no variations in the gravitation of it. So, it was it's a small problem. I thought it would be interesting to solve this. Okay, so let's say I will write some important details about this problem. So you with the They have given rocket mass, which is nothing but the structural mass plus the payload mass, which is around 1000 kgs. That is what they have given. And also they have given the mass of propellant, which is around 1500 kgs. Now the propellant is consumed at a constant rate of 100 kg per second, which is m dot. M dot is nothing but 100 kgs per second. What else is given? The ISP of the rocket is given, specific impulse of the rocket, which is around 1500 newton second per kg, which you can also write it as meters per second. Okay, newton second per kg is nothing but, which you can replace it as newton meters per second. So can anyone tell me what is this ISP? What does it signify? Why we need to know ISP of the rocket?
So it can be considered a measure of characteristic fuel efficiency, means how much impulse we are getting per unit propellant burn.
Okay, okay, that is right. It's like an.
Equal to efflux velocity.
Can you repeat, Tanisha?
Sir, it can be equal to efflux velocity. Uh,
Okay. The other one was impulse by mass of propellant, and we have the telling average. It's like average of rocket, like mileage in car. So it's interesting. So like mileage in car. Okay. So I don't know whether others understood what Teeth is telling.
Yes, sir. Got it.
So if you think about it, so basically you guys gave the answers. The answers were right. Um, but few important things about ISP is nothing but this is uh, m dot into mass flow rate of the propellant. So this is also one of the you know formula for ISP. Uh, so what this means is why ISP is very important is it actually gives us the mileage of the rocket. So that's what Teeth is telling. So it is telling. So our interest is we need to get as much thrust as possible. That is our interest from. That is our Uh, interest of doing so the reason to do all this work is I need to put something in the space, and for that I need to give some force, and that force is called thrust. So my interest is to maximize this thrust, but how this thrust is obtained, it is obtained from burning the propellant. So let's say if I could get large amount of thrust, let's say with a small amount of propellant, so that is what I call it as a very high performance rocket. Okay, so basically ISP is the um, it's a figure of merit for the rocket. Okay, please understand. So this is the ISP is going to determine whether that rocket is useful or not. So let's say if you have a low ISP compared to the present rockets, people are not going to use that rocket, whatever you develop. So the ISP is defined for like solid propellant motor or liquid propellant engine, whichever rocket you come up with, let's say electric propulsion, whichever rocket you come up with, everyone is going to ask what is your ISP? What is the ISP of this rocket? What is it going to give? So only if that is high, people are going to accept it. So it is like a figure of merit for the performance of the rocket, and we always want to maximize it. So that is why Teeth also mentioned this. It's like a mileage for car. How much in car? What we are interested in? How much kilometer I can move, I can go per liter of the propellant, right? Kilometer per liter. Uh, so basically, the same thing if you just convert, what is the thrust I'm going to get per mass flow rate of the propellant? And this is also actually, written as thrust per weight flow rate of the propellant, or you can also, I would not press. put equal to. So you can write it like P into G naught. This is also people usually used to write and express it in terms of seconds. Okay. So usually, let's say if you take a solid propellant rocket, it have like around 260 seconds of ISP, and if you take a liquid propellant rocket, it might be around 400 seconds of ISP. So if you compare between these two, what do we have is we have solid propellant performance is better than the liquid propellant. Okay, so I'm sorry, it's the reverse. So liquid propellant performance is better than solid propellant because it has more ISP. So that is the advantage liquid propellant provides. But liquid propellant also have certain disadvantages. Can anyone say what are the problems with liquid propellant? If liquid propellant performs better, why not we use liquid propellant itself? Why to use solid propellant?
Sir, efficiency will depend upon density. Liquid propellants have low density than solid.
Okay, that is right. Any other concerns? Density, important thing. Um, Thanks for bringing this up. Why density has to depend. So let's say we'll come back to density again. What is a what are the other concerns we are in? You know, we are looking for in why not use a liquid propellant? Any other concerns you guys can think of? Okay. What I would do, I will tell you. This is actually an important concern. It's a safety. Doesn't mean solid propellant doesn't blow up, but liquid propellant has a more tendency to blow up. I mean, the rocket can burst out. So the reason is it can have a
So the
leakage.
solid propellants don't actually undergo combustion in the solid form. Actual, they are converted into liquid and then they in the engine, I
Okay.
guess.
Okay,
So that's
so
why safety is better.
I mean, even in solid propellant accidents can happen. Doesn't
Okay,
mean you
can.
cannot rule out, but it is better in terms of in solid propellant than liquid propellant. The reason is you might have a small leakage in the tanks, and also the construction. Another important thing is construction. So what you need for a solid liquid propellant is you will have a you need to have a tank, you need to have a pump because you need to pump the liquid at higher temperature, and then you are combusting it. So it's very complex in constructions. So let's say for example, let me just draw a liquid propellant engine. So there will be actually my drawing is very bad. So what you have is you have something like this. So from here, what happens? Some liquid is coming from here. Another liquid will come. Okay. So what really happens is this will be fuel. This which will also be in liquid form. Okay. And this will be oxidizer, which will also be in liquid form. For example, liquid hydrogen and oxygen. Let's say for example. Now what happens? You need to carry this. You need to carry these tanks. These are nothing but tanks. Fuel tank and oxidizer tank. You need to carry this tank, and then if the pressure if you want higher pressure in the combustion chamber, higher pressure actually leads to higher performance, which you will come to know sooner when you are studying those chapters. So you need a pump to increase its pressure, right? So what you will put is you will put a pump here and here. So you'll put a pump, and be fuel pump, and there will be oxidizer pump, and it will go together inside the combustion chamber, and it will mix, and then it will combust and it comes out. Okay, so what you have is you have tanks, you have pumps, and then you have combustion chamber, which is very complex, and also you have lot of pipings, right? And if there is any leakage in the tanks, it's going to be bad for you. And this safety and construction is the main problem with the liquid propellant engine. Whereas if you go to a solid propellant engine, solid propellant rocket, so it's going to be just simply like this. You will just cast the propellant inside, then you will just ignite it. You'll just ignite it, so it just starts burning and comes out. So there is no motion of, there is no, you don't need to move the propellant inside outside. You don't need to have a pump, you don't need to have anything, but you can just simply ignite it, and it is going to go away. So that is, in terms of safety and construction, this is going to be better. Okay, but important thing is this thing, density. So why uh, interested in density?
More fuel and less volume for solid.
Right. So what you have is what you're trying to do is you're going to, for the same mass, you don't want your rocket to be very big, right? If it is small and compact, it's nice in terms of other aerodynamic perspective. So that's why density is also one of the reasons. But there is also there are also problems with solid rocket motor. Can anyone tell what is the problem with solid rocket motor? So one is, as I said, low ISP compared to the liquid propellants. Low ISP, low performance. What is the other one?
So storage can be a problem. Yes.
What we said now. So density is good, right?
No, this for this solid propellant storage is often a problem because cryogenic fuel is used.
Cryogenic
So
is not solid propellant. Okay, I think there is a. See, cryogenic is actually liquid propellant engines. Right? Cryogenic is what?
okay,
Cryogenic is not solid. It's liquid hydrogen and liquid oxygen. It's actually LH2NOx. This is the cryogenic propellant. The hydrogen and oxygen will be liquid only at cryogenic temperatures like 20 Kelvin and 80 Kelvins. So hydrogen and oxygen, you cannot have it as a liquid form above that. So cryogenic is actually a liquid propellant engine. The solid propellant engine here, solid propellant motor is actually the propellant will be solid. Okay, it will be, they will mix the propellant, they will cast it into, it's like same like metal casting. They will cast it, and then they just put it inside. That's all. That's what they do. Any idea what could be the problem? So one important thing is you don't want the thrust to randomly vary, right? You want to control it. You want to control the thrust. You want to control. So it's all about precise operation. How you want to do it. It's not like just if you switch it on, there is no way you can stop this combustion, whatever. So once you ignite it, the gases comes out. Okay. Let's say any gases. Let's say CO2, H2, any gases, H2O, any gas, whichever comes out, it's going to go in, and the surface which got ignited, it is not going to stop until the whole propellant is consumed. You cannot switch it off. There is no control, basically. So you cannot control it. solid propellant. Once you ignite it, it's gone. So after that, you it's just waste. So once all the propellant is, it will not stop until all the propellant is consumed. So that is the thing. But in liquid propellant, that's not the state. It's, that's not the thing. So what you do is you will have some mass flow rate of the fuel, and you will have some mass flow rate of oxidizer, and you will have a valve, and you can control it. If you close it off, there is no thrust. If you increase it, the mass flow rate keeps increasing, and you will have a lot of gases coming out. The thrust will be higher. So you have that control basically. If you are in a liquid propulsion system, in solid propulsion system, you do not have that. That is one of the problem with solid propellant. So that's why both of them have its own merits and demerits, and we need to use it based on the experience we have. We need to properly make it work together. So you cannot ignore one with the, you cannot go for one because of the its advantages, or you cannot remove one because of its disadvantages. So we have a question here: do liquid propellant have high calorific value? It depends upon the propellant, which propellant we are talking about. All liquid propellants, you cannot say it has high calorific value. Um yeah, you will learn about it more. So what is really this calorific value? How do they characterize a propellant? All these things you will learn about it soon. Okay. So yeah, coming back to ISP. So ISP is like a main performance parameter which you should know, which you should keep in mind. Any rocket you design or you come up with, people are going to just ask what is ISP. Only if it is higher than the present model, then only they are going to go for it. Okay. So, and whatever you guys said, everything is right. So let's see. Let's say we have ISP, and what we have to find the acceleration of the rocket at liftoff, 10 seconds after liftoff, and just before burnout. Let's quickly solve this problem. So, okay, let me again draw the schematic of rocket. So this is the, let's say, center of mass, and weight is acting downwards, mass into G, and then thrust is acting up. Okay, these are the only two forces, I guess. So we were assumed to do the vertical flight and no variations in the gravitational field. That is also an assumption. In reality, it's not the case, right? So once you start the propellant, you are going to reach higher altitudes, and g's keep on going to vary. Okay, let's say for now, for this problem, we'll assume that. And what we will do, I think we already did in last class also. We'll just continue that. It's going to be Newton's second law. We are going to apply Newton's second law to it, which is going to be summation of F is equal to mass into acceleration. And what are the F's we have? Sorry. Right. So uh, let's say if you consider upward as a positive, you can consider F minus mg is equal to ma. We are interested is we need to find acceleration, so this can be written as F minus mg by m. So now the important thing is what is this m? How we are going to calculate is the important thing. So let's say at liftoff, so acceleration, let me mark it as 1, let's say. It's going to be F minus mg by m. What is going to be F? What is going to be m? So F we can, how we can find F?
So, yes, sir.
Yeah. So we can find using the
Mass flow rate into the specific impulse.
true mass flow rate into specific impulse. Let's say mass m dot into ISV, which is around, I think m dot is 100 kgs per second and ISV is around 1500 meters per second. What is the F you are getting? It should be
150 kilonewton.
true 150 kilonewton. Okay. Now, what is the mass at the liftoff?
So 2500 kg.
Right.
Assuming no payload. Structural and plus the propellant. No
Hmm.
payload.
So, actually, what we considered was the rocket mass we gave, right? So that we added as 1000 kgs includes payload. So that's what we considered. So let's say if you assume payload and structure is included together, then that is going to be 1000 kgs. Plus at the liftoff, you have all the propellant loaded, so it's going to be plus 1500. So it's going to be 2500. So now let's say if we calculate this, what is the acceleration we are getting?
50.19 meters per second.
3.19 meters per second square. Okay, now at 10 seconds. What is going to be my mass at 10 seconds? So A2, let's say, or A at t is equal to 10 seconds is again equal to F minus m at t equal to 10 seconds g by m at t equal to 10 seconds. This is what we need to find. F also at t equal to 10 seconds. What are these F at t equal to 10 seconds and m at t equal to 10 seconds? Will it vary or we should just keep it constant? And if I just keep it constant, why they even ask that question, right? Let's ask one question at a time. What is the thrust at 10 seconds? Is it going to be any different compared to the
Thrust. I guess the thrust will remain the same
right?
since mass flow rate is not changing,
Hmm.
and so it's not specific impulse.
Right. So basically, for the entire duration of operation of rocket motor, the mass flow rate is not changing, and since mass flow rate is not changing, thrust is also not going to change. So that is why it's going to be 150 kilonewtons. Oh, what should be the mass at 10 seconds? So you will definitely have the mu plus ms 1000 kgs plus you need to have propellant. What is the propellant we should have?
So it will be 500 kgs, I think.
Right. So,
Propellant left.
so you should calculate what is the propellant left. Let's say this is the propellant at t equal to 10 seconds. What is the propellant left? Okay.
Yes,
How
sir.
do we calculate propellant left at t equal to 10 seconds? It's going to be the initial propellant mass minus mass flow rate
Minus mass
is,
flow rate. Yes, sir.
yeah, right, mass flow
Into
rate
time.
into time.
Into time.
So if this is the case, then it is going to be 100 into 10 seconds, which is around 500 kgs. That is what Akhileshwar told. So if that is the case, then you can find mass at 10 seconds. The rocket motor's mass at 10 seconds is going to be 1500 kgs.
1500. Yes, sir.
True. So this is 150 kilonewton. minus 1500 times 9.81 divided by 1500. That is going to be your acceleration at 10 seconds. How much?
90.19 meters per second.
Okay, wonderful. So 90.19 meters per second square.
Square.
And at burnout, at burnout, uh,
All fuel consumed, I guess.
right. So dB, let's say. Then you have F minus mg m burnout divided by m burnout. So the all fuel is consumed. So it's going to be the remaining mass is going to be just structural mass plus payload mass, which is around 1000 kgs. And again, thrust is going to
So
remain same.
thrust will be there or not means at burnout.
Yeah, you tell me what will be the thrust.
Means if all the fuel is consumed, then I guess thrust becomes zero.
Thrust becomes v zero after the
All
burnout.
fuel at burnout means the last push it will have
Right. After the burnout, thrust will become zero.
just
What
before
they
burnout.
have asked is just before the burnout. So what should be the thrust? So it's been asked this just before the burnout. What is the thrust?
So it will remain the same 150
So
kilonewton then
right.
because then
So if it is, so it yeah. Since you came up with this question, so you should be careful with the question, whether it is been asked after the burnout or just before the burnout. If it is just before the burnout, the force is still acting because propellant are burning and then it's going to come out. It's just the last set of propellant is coming out. Okay, and so the thrust will be produced based on that propellant, and that is going to remain same because mass flow rate is same. So if that is the case, 150 into 10 power 3 minus 1000 into 9.81. How much is this coming out to be? 2000.
so 140.19.
40.19 meters per second square. So as you can see, the acceleration is keep on changing or keep on increasing uh, during the operation, right? T equal to 0. During the operation, not because of force is changing, but because the mass of the rocket is changing. That is why this question is interesting. When we have a
So
same force,
even
yes,
so now even if we will consider the reduction in g, we will get even greater acceleration, I guess.
true. So if we consider reduction in g, yeah, we will get greater acceleration. So basically, not because the force is changing, not because force is getting increased or decreased, it's because the mass of the rocket itself is changing, which is causing the acceleration to, increase. So that is why it's also a unique problem. So I hope you guys understood this question also. I do not have any more questions. This is the same questions I just solved it before the class. Maybe you can use it for your references. I mean, we got the same results only. That's all right. So yeah, do you have any questions regarding the problems we solved today, or if you regarding the assignments or lecture materials, you
Yes,
can ask me.
in assignment 2, I'm having a problem. Assignment
Which
2, question 17.
question 17?
Assignment 2.
Mm, assignment 2. Question number 17. The maximum height the object will reach in kilometer expressed in one decimal piece. Okay, so I think it's a linked question. An object of mass 5 kg is projected from the surface of Earth with a velocity that is 25% of the escape velocity. Answer the following and suitably fill in the blanks in the units indicated. Okay, so what is the problem you are facing, Akhilesh?
So the answer I'm getting is lesser than what is specified in the range. I'm getting like 397.9 kilometers,
So,
but it's even 420. 420 to
okay,
430 it must be.
I think this is, so the results are released. So you might have the
So I'm not
solution.
able to find the solution. No, even in the discussion forum they said solution is given, but I'm unable to find the solution.
I see. Okay, okay, okay. It's not here, no? Yeah.
Not yet. Yeah.
So usually the solution comes here, or
Yes, sir. Yeah, it used to come even the previous courses that I have done. It used to
right,
come,
right, right. So
but I guess it comes to a few days later.
see, okay. So anyway, let's try to solve it. Uh, maybe you might be right. Let's try to solve it. Object of mass 5 kg is projected. So let's see what I'm getting. Mass is 5 kg projected with 25% of the escape velocity. So velocity is 0.25 times the escape velocity. And what is the maximum height it will reach? Is that what they are telling? This
Yes,
is
sir.
what they are telling, right? That's all, nothing else. So what you have is you have some mass. It is going up. This mass is 5 kg, and it's going up with some initial velocity vi. And what the force acting on it is only mass mg, right? So then you can write. Mm, or actually, you don't need to do force balance. Maybe you can do energy balance, right? So you can write kinetic energy of the initial kinetic energy is equal to the potential energy. Is that how you did?
Yes, sir. The initial kinetic energy, the velocity is 25% the escape velocity. So,
Okay.
and that's
So it
divided.
will be mg into h, right?
Yes, sir.
This h is what we were asked to find. So 0.25 ve square divided by 2g.
Yes, sir.
Answer the following suitably fill in the blanks in the units indicated. So is this what you did? What is the escape velocity? How do you find it?
So I use the formula that escape velocity is under root 2 gme upon re.
That what escape
So
velocity is?
root 2, 2 is also there inside the under root.
2 gme by re. Okay, what is the escape velocity you are getting? So 11.2 kilometers per second is for Earth, I feel, right?
Yes, approximately it's that.
Let's say if I just take that square divided by 2
So the
divided by
actually the initial velocity, the 25% of it that I was getting was 2.79 kilometers per second.
2.8 I
20%.
was getting.
Yeah,
Right.
yeah, 2.8. Because
So what is the in kilometers they were asking? This is 0.25 into 11.2 square divided by 2. 11.2 is kilometers per second. 10 per 3 into 9.81. So is this what you are getting, like 399.59 kilometers per second?
Yeah, I was getting like 397.
So it's given 420 to
420 to
430.
430. Yes, sir.
Okay, but what we did is we consider g to be 9.81 meters per second square, but as it goes above, the g decreases, right? So did you, if you if you consider it, the results will vary.
Yeah, the G would reduce and H will increase.
Okay, so
But okay,
how do we do it? Let's say from initial velocity to the final velocity, which is going to be 0, uh, mv dv is equal to integral of mg ph 0 to h, right? And g, how can we write g? So did you, have you tried this, or did anyone
no,
in
sir,
the,
I did not. I did not do this. I took it
okay,
as G constant.
okay. So did anyone in the call, they have they tried it? Like no one tried it, is it? So how can you write g as a function of h? Uh, Sometimes it is not on top of my head, but potential energy can be written as so this is also can be written as integral of re to r, or which is re plus h into g m e m by r square dr, right? So let's say if I integrate it, you will get gme m into 1 by re minus 1 by r is equal to, this v is constantly reducing. Okay, so m and m can get cancelled, so maybe vi square by 2 is the initial kinetic energy into m, so m gets cancelled. um, vi is 0.25 times ve square by 2 equal to gme into 1 by re minus 1 by re plus h. So did you say this is coming out to be 0.25 into 11.2 into 10 power 3 square divided by 2? So this side is coming out to be 3.92 into 10 power 6 is equal to, what is GME? I think it's G and ME are given, I guess. 6.67 something. 6.67 into 10 power minus 11. 6.67 into 10 power minus 11. Mass of Earth 5.97 into 10 power 24. I think it's 6 9. How much is the radius of Earth? 6378. 6378.1 into 10 power 3. So how much is this R coming out to be? Divided by 6.67 divided by 10 power minus 11. 4. 378. Yeah, I'm doing some algebraic mistake. Uh, is this right till here?
Yes, it appears to be.
Okay, so how this is coming out to be 9.84 into 10 to the minus 9 into 50. What is this? 3 minus 1 by r.
Yes, so by this it has come out to be 425.4 kilometers.
Okay,
The
so
H value of H. This
this
is
much
6.
kilometer.
Yeah,
So let's
I'm
say
getting or 425.
6378.1. 427 you are getting. Okay.
Yeah, yeah,
So H is 427.
yeah.
So actually you should be little careful.
Got it.
Interesting. 420 to 430. Okay. That's fine. So if that is the case, is your increase in potential energy is also incorrect? Did you?
No, so that was correct. Means the increase in potential energy will be exactly equal to what it was given an initial kinetic energy.
Oh, okay, okay, okay,
So
okay. Mm-hmm.
so it just turned out to be 19.5 exactly. I no need to calculate. I didn't calculate. I just wrote it as it is.
Okay, okay, okay. Interesting. Right. Nice. Any other questions?
So question 9 I was not able to figure out actually in this same.
Okay, let's see. Question 9. Question 9. Okay. After completing the Apollo mission, the astronauts has to leave the lunar module named Eagle. The lunar module had to dock with command module named Columbia, which was orbiting at altitude of 150 kilometers. The total ideal velocity increment required to. So I think this was a problem, no? You guys mentioned it before. I remember. So were you getting like a very low total ideal velocity increment? Sure, maybe you are muted.
Yes, yes.
So you were getting low total velocity increment, right? So probably it should be around 1.75 kilometers per second. Was it?
No, for the answer it is given it is 5,520 meters per second.
Yeah, but how much you are getting?
Yeah, I was getting less, much less. So I was unable to mark it.
So yeah. So actually, I think it's a problem with the question. It should be around 1.75 kilometers per second or 1745 meters per second. They will update it. They will update it sooner. Okay.
Alright, sir.
So this is from the moon surface to the Eagle module, right? Moon
Yes, sir.
surface.
Sir,
So
I was
that is
getting 5,400.
5,400. Interesting. So So problem with the question. So what was given is 150 kilometers. 5400 was also not in the options.
Sir, one more question I have doubt.
So let's try to finalize this also, since you got 5400. So this is the total ideal velocity increment they were asking, right? So you can just directly use the from lunar surface to the module which is at 150 kilometers. So you can directly use the total velocity requirement equation. So it is around uh, I think this is what I think this is the equation, right? Just instead of mass of earth you just replace with mass of moon, so it is going to be 6.67 into 10 power minus 11. Mass of moon is given, what is given, 7347 into 10 power 22, 7.347 to radius of the moon, 1737.4, 1737.4 into 10 power 3 plus 300 into 10 power 3 divided by 737.4 into 10 power 3 into 1737.4 into 10 power 3. See how much I'm getting. 6 7 into 10 power minus 11, 5 7 3 4 7 into 10 power 22, 173.
So by this I'm getting 1.745
Okay,
kilometers per second.
okay. Just give me a minute. I will also try to do the calculation. 3 square root of 1. Yeah, so I'm also getting 11745 meters per second. Okay, Tanisha also told the same thing. Okay, I think that solves the confusion. Maybe they will update the solution key also. At that time they will update the marking also. No need to worry about it. Okay. What was the other question you had problem, Tanisha? I think Tanisha was the one asked.
Sir, I think it is question number two. With increase in altitude, what will be the change in total orbital velocity?
The orbital velocity required for orbiting bodies about any planet increases with increase in altitude above the Earth's surface. Is it true or false? Answer is false. The orbital velocity usually has to decrease, right, when you increase the altitude. Do you have do you have doubts on it?
Sir, actually, I have marked false, but it had given it incorrect.
But accepted answer says false. Still, it was incorrect for you.
So even I had marked false, but it is showing correct for me. This is some error with the system, I guess now.
So you no need to worry about it. If this is an error in the system, you can just uh, you can just put you can just tell that I marked false, but the score was given zero for me. I mean, I marked the correct answer, but the score was given zero for me. You can just mail NPTEL also if you want, or they will itself correct it sooner. So you no need to worry about it. So they have to upload the solution key, right? When they upload the solution key, they will do all the corrections. So was that a technical, is that a technical problem you are facing, Tanisha, or is it showing accepted answer as true in your portal?
Yes, sir.
Second question.
Yes, sir. Accepted answer is true. It was showing.
I see. Hmm. What you do is you send an email, okay? You tell that this is for a. I mean, for me also it's showing false. I don't know for why it is showing true for you. Maybe some problem with the system. They will change that. You don't need to worry. So you can just send an email telling that this is what it has been showing to me. Please help me out. Something like that. You can just mail. So they will take care. No need to worry. Any other questions you have?
No, sir. As of now, no.
Okay. Anyone else have any questions? All right. So if there are no questions, maybe I will stop here. You can we can meet next week. We will visit the nozzle theory. Nozzle. We can discuss about nozzle problems, and also performance of nozzle. How do you quantify it? All those things we will see in the next week. So if you have questions, you can stay back and ask. If you don't have questions, we'll meet next week. Thank you.
Thank you very much, sir.
Thank you.
Thank you, sir.
Thank you, Krishna Kumar.